Hello everyone. In this video of chapter transition and inner transition elements, I'll be talking about the compounds of potassium permanganate and potassium dichromate. Then I'll be talking about their properties also and the metallurgy part. And in metallurgy, I'll be talking about the extraction of iron metal. Now the compounds of manganese, which is potassium permanganate, KMnO4 is the chemical formula, and the compound of chromium, which is potassium dichromate, which is K2Cr2O7. Let's start with potassium permanganate first. The preparation of potassium permanganate, it used to be done by when you are taking finely divided manganese dioxide and it is heated with KOH, which is also called as caustic potash, and an oxidizing agent, which is potassium chlorate. Then what will happen in the first step, you will get potassium magnate with chemical formula K2MnO4, and in the neutral acidic medium the green potassium magnate disproponate in KMnO4 and manganese dioxide. Here potassium magnate will be treated with carbon dioxide and water to give potassium permanganate, manganese dioxide and potassium bicarbonate. This liquid would be filtered through the glass bowl or the sintered glass and evaporated till the crystallization occurs. Potassium permanganate used to form the crystal, which are deep violet in color or maybe black in appearance. Now the electrolytic reduction. In electrolytic reduction, the alkaline solution of potassium magnate will be taken and it is electrolyzed between the ion electrodes, used to be separated by diaphragm, and this would be the overall reaction where potassium magnate is going to be converted into potassium permanganate along with the KOH, which is a byproduct. The oxygen involved, or you can say it is evolved at the anode and convert this magnate to permanganate ion, and the solution is again filtered, evaporated to get the deep purple color crystals of KMnO4. Let's talk about the chemical properties of KMnO4. KMnO4 in acidic medium. In acidic medium, it is wonderful oxidizing agent, and it used to oxidize iodide ion into iodine, or you can say I-1 to I2, where KMnO4 permanganate ion will turn up itself to manganese ion and iodide will be turned up into iodine. It used to convert ferrous to ferric, and itself it used to convert into manganese ion. It used to convert hydrogen sulfide to sulfur. Again, it will itself convert into manganese ion, and oxalic acid would be converted in acidic medium of KMnO4 to carbon dioxide. In neutral weakly acidic medium, what will happen? The oxidation of iodide will be happen and iodate ion would be formed. This is the chemical reaction involved where in the neutral medium, that means potassium permanganate is dissolved in water and treated with the iodide salts to convert into iodate. Itself it will convert into manganese dioxide and KOH generally form. Thiosulfate in neutral medium used to be converted into sulfate, and the manganese salt used to oxidize into manganese dioxide. Now the next is the uses of KMnO4. KMnO4 is used as an antiseptic for unsaturation test in laboratory, in volumetric analysis as of reducing agent, for detecting halides in qualitative analysis. It is one of the powerful oxidizing agent in the laboratory and industry. Now K2Cr2O7, its preparation. In industrial production finely divided chromite ore with chemical formula FeO.Cr2O3 is used to be heated with anhydrous Na2CO3 and the flux of lime in air in a reverberatory furnace, a special kind of furnace where this this chromite ore used to be oxidize with the help of oxygen and sodium carbonate to convert it into Na2CrO4, ferric oxide and carbon dioxide gas. Now this sodium chromate used to be formed is extracted and it will be treated with concentrated sulfuric acid to give you sodium dichromate along with NaCl and sodium dichromate hydrated water also. Addition of potassium chloride to the concentrated solution of sodium dichromate, the double displacement reaction happen and potassium dichromate will fall. This is the preparatory method of P2Cr2O7. Its chemical properties: oxidation of iodide from aqueous solution of KFI by acidified K2Cr2O7, it will give you I2, just like we have heard in acidic solution of KMnO4. Same it is happening with here also. H2S will be converted into sulfur with the treatment of acidified K2Cr2O7. Then the common properties, let's suppose I am talking about these are the common properties. Common properties are physical property: D block elements are lustrous and shining, they are hard, they have high density, they have high melting boiling points, they are good electrical and thermoconductors, they have high tensile strength, they can form alloy with transition elements. Chemical properties, you can talk about all are electropositive, they have variable valency, they are good reducing agent, they form insoluble hydroxide oxide, and they are also a very good catalyst in so many biological reactions. If we are talking about their differences, most property exhibited by the D block elements are used to be similar with the F block also. The elements of the first row used to differ from the second and third row in stabilization of higher oxidation state and their compounds. For example, molybdenum 5 and tungsten 6 compounds are more stable than chromium 6 and manganese 8. Higher oxidation state for the element in first row is +7 and in case of third row is +8 as in RuO4 and osmium tetroxide. Let's talk about the extraction of metals now. The naturally occurring substance which is found in a earth crust, a naturally occurring substance in a compound form which is coming in from the earth crust is called as mineral. There are so many minerals, and the mineral which is containing high percentage of metal and from which the metal can be extracted economically and profitably is called ore. This is the list of so many minerals of iron and copper and zinc, but out of these many minerals we used to consider hematite as a ore of iron, chalcopyrite and chalcocite are the ores of copper, zinc blende is the ore of zinc. Metallurgy: commercial extraction of metals from their ore is called metallurgy. Different methods are used for their extraction depending upon the nature of metal and its ore. Pyrometallurgy is the process where the ore is reduced to the metal at higher temperature using reducing agent like carbon, hydrogen, aluminum, etc. Hydrometallurgy is the one where the extracting of metal is happening in the aqueous solution using suitable reducing agent. And electrometallurgy is the one where the metal is extracted by the electrolytic reduction method from its molten state. Now what all are the steps involved in the process of extraction? The first step is the concentration. After mining the ore from the earth crust, it is subjected to the concentration. In this step, we used to remove the soil, sand or mica kind of impurities which are called as gangue. And if I want to define gangue, it would be the sand, mud or other unwanted properties which remain mixed with the ore are called gangue. During this process, the ore is separated from the gangue material, and for concentration, we used to employ so many methods like washing, hydraulic classification, magnetic separation, flotation, etc. Now, next is the extraction of iron from hematite using blast furnace. This is the composition of hematite ore. Here, silica, aluminum oxide, and some phosphates are present along with Fe2O3, and Fe2O3 is ore here. These two are GAN. Now, iron is extracted from hematite ore by its reduction using coke and limestone. Carbon in limestone is reduced to carbon. Carbon in limestone is reduced to carbon monoxide, and carbon monoxide further reduce iron oxide into metallic iron. Limestone will act as a flux. It combined with GAN material to form the molten slag, which could be removed from the bottom part of the blast furnace. The first step would be the concentration. In concentration, what we used to do, we used to remove the GAN particle by washing the ore with the current of water. In the hydraulic classifier, the GAN particles will be flow away, and the lighter GAN particles are being removed in this part. We used to do the concentration with the help of magnetic separation also. If we have the particles which are magnetic in nature, the iron particle will be attracted by the magnetic, and other GAN particles would be removed. Gravity separation method, fourth flotation method, leaching could be employed. Particularly, fourth flotation used to be employed for the sulfide ores. The next step would be the roasting part, where iron oxide would be taken, and the sulfur and arsenic impurities would be removed in these steps, because the iron ore would be heated strongly in the oxygen atmosphere, and sulfur and arsenic oxides will be removed in the form of their oxides, because they are gaseous. The next step would be the reduction step, which is also called the smelting step. In this step, the iron oxide will be taken into the furnace, which is called as blast furnace. Here it is, blast furnace. And blast furnace is a tall cylindrical structure uh, which is made up of steel, and the inner lining is of refractory bricks. The height of typical blast furnace is 25 meter, and the diameter would be around in between 5 to 10 meter. The furnace works on the counter current of principle, where the charge comes down and the hot gases move up in the charge means the mixture of ore, limestone and coke. It is coming from cup and cone from the up, and blast air and oxygen used to be going up from the bottom of the blast furnace. It is comprised of, this furnace is comprised of three parts. First is hearth, second is wash, and third is stack. The charge containing ore, limestone introduced from the into the furnace by cup and cone arrangement. This is cup and cone arrangement here. In this arrangement, the cone enables uniform distribution of charge, and the cup prevents the loss of the gases, because we used to use gas multiple times. Blast furnace used to be preheated, and these are the temperature which are mentioned here, which is happening or which are maintaining into the blast furnace. The charge and hot air will come in contact with the uh, with the with the substances which are coming from the cup and cone arrangement down. Now we will talk about the reaction in the blast furnace. There are different temperature zones in the blast furnace. The temperature goes on increasing from top to bottom in the blast furnace. At the top, the temperature is 500 Kelvin, and maximum temperature in the furnace is 2000 Kelvin. First zone is zone of combustion. In zone of combustion, this is 5 to 10 meter above from the bottom. So you can say this is zone of combustion, and in this zone the reaction used to happen is carbon monoxide formation, and further the formation of carbon dioxide, and this is happening at this temperature, you can say around 2000 Kelvin. These two reaction is happening in the zone of combustion. Now the zone of reduction is, here the temperature is 900 Kelvin, And here what will happen, the carbon monoxide is going to reduce this iron oxide into iron, or iron oxide is going to be reduced by carbon monoxide into iron. And the last third zone is the zone of reduction, where sorry the last zone is the zone of slag formation. Not last, second last zone is the zone of slag formation, where the calcium carbonate would be decomposing to give you calcium oxide and carbon dioxide. Calcium oxide will combine to silica to give you the slag, which is calcium silicate. And also calcium aluminate is also a slag which used to be removed from the bottom of the furnace. And the last zone is the zone of fusion. Manganese dioxide and calcium phosphate used to be present in iron, and they are reduced in manganese and phosphorus. Some of the silica is also reduced in Si. The spongy iron coming down in the furnace melts absorb the impurity of carbon, silicon, manganese, phosphorus, sulfur. So the molten iron correct from the bottom of the furnace, and molten slag will be collected from the separate outlet. Molten iron is poured into the molds so that they will solidify, and the blocks which used to form after solidification are called pig, or you can say pig iron. It is containing 4% of carbon, and the pig iron is remelted, and it would be cooled down to turn up into the cast iron. The waste gases, carbon monoxide, carbon dioxide used to escape, and finally the iron which is coming out, which is also called the cast iron, would be refined. Used to be refined by electrolytic refining method. The choice of extraction technique is governed by the following factors. Number one is nature of ore, availability of the cost of reducing agent. Generally, we used to use coke because it is quite cheap. Then the availability of hydraulic power. Then purity of product is mandatory. Value of byproduct, for example, sulfur dioxide is obtained during the roasting of sulfide ore, is the very important compound to manufacture sulfuric acid on the large scale. And knowledge of electrochemical series provide the solution to many problems. Now the another thing which we need to learn is what all are the commercial forms of iron, and the commercial forms of iron is cast, wrought and steel. Wrought iron is the purest form of iron, and steel, you all know, it is an alloy of iron, carbon and some metal like nickel and nickel. Here there is a difference in between the cast iron, wrought iron and steel. Cast iron is hard and brittle, wrought iron is soft, and steel is intermediate between the cast and wrought iron in terms of hardness. It is containing 4% of carbon. Wrought iron is containing less than 0.2% carbon. It contains carbon 0.2 to 2%. Cast iron used for making pipes, manufacturing of automotive parts, pots and pans and utensils. It is Wrought iron is used to making pipes, bars, tables, engine boards and rivets. Steel is used in the building infrastructures, tools, ships, automobiles and boats. This is all about iron. Thank you.